Hello everyone. Thank you for joining us. This webinar is hosted by ED808. I would like to thank everyone to join this webinar. I hope everything goes well. During the webinar, if you have any questions, please use the chat area to ask questions, and I will try to answer your questions as soon as possible. Let me first introduce you myself. My name is Bahadir Sadan. I'm a Turkish civil engineer. I have finished my degree in Turkey and also my master's degree on earthquake engineering in Turkey. Then I moved to Italy for a PhD in Politecnico di Milano on structural, seismic, and geotechnical engineering. Afterwards, I returned back to Turkey, and I started working in some companies in Turkey, and established my own company, OBS, Earthquake Engineering Solutions, and I have been doing structural engineering and also engineering design and also consultancy on earthquake engineering problems. At the same time, I'm a part-time lecturer at, I'm part-time faculty member of MEF University in Istanbul, and also a board member of Turkish Association for Seismic Isolation. If you have any questions after this webinar, you can also send me an email through the email shown below from bahadir@obs.com.tr. I will be happy to answer any of your questions. This webinar will give you an idea of what seismic isolation is and why we need seismic isolation in general. It will be composed of two parts. In the first part, it will be very general earthquake engineering knowledge, where I will tell you about the tectonic structure of the earth and why earthquakes occur. Then I will try to tell you a little bit about the seismic design philosophy, and at the end we will see why we need seismic isolation. Then in the second part, is the main part of this presentation, I will talk about the basics of seismic isolation, the history of seismic isolation, the main isolator types, seismic isolator tests, and the testing facilities worldwide, and some of the applications, again, seismic isolation applications in the world. This part I will pass very quickly. Probably you all know what I am talking about. The earthquakes occur because of the movement of the tectonic plates. Every day there are several earthquakes, and every year there are several major earthquakes that happen, and the buildings and the people suffer from those earthquakes. This slide shows the major tectonic plates movements. The largest earthquakes occur in this part of the world, in the east of Asia, near Japan, and west of the continent America, where we call this area a ring of fire. And the largest recorded earthquakes mostly occur in this part of the world. When we check the major earthquakes on the world, which are larger than 8.5, this is the top 12. You can see that what we have seen up to this moment is not more than 9.5 magnitude earthquake. And the scenario is this. You can see the images of the destructions after earthquakes in Chile, in Japan with tsunami, in again Chile in 1960, 9.5 earthquake. In Indonesia, again a big tsunami hit the coast after the earthquake. And this is the view from the earthquake history of the Europe. As you can see, the most of the earthquakes occur in the Eastern Mediterranean area, where I also live, in Turkey, in Greece, in Italy. The most of the largest earthquakes happen in this region, and the results are again due to our building stock very catastrophic. These images are from 1999 Turkish earthquakes in Izmit area, Izmit and Düzce area, where we see the total building collapses and some also failures of ground, liquefaction, and nearly 30 years passed from this earthquake, and I think the building stock did not change a lot, and we can experience something very similar very soon. And in these earthquakes in 1999, more than 30,000 people died in Istanbul. And that was the moment in 1999 that I decided to be an earthquake engineer, and I also started working on seismic isolation. So first I would like to talk generally about seismic design philosophy and how the buildings react to the seismic excitations. When an earthquake occurs, the ground moves. And when the ground moves, the earthquake forces act from the mass inertia center of the building. And due to this earthquake load, some internal mechanisms occur in the structural elements like columns, beams. Here is an example of a bridge pier, double band bridge pier, that the force acts from the mass center, and the result is the shear forces on the bridge piers. What you can do, how you design this building, according to the conventional seismic design philosophy, is you can do an elastic design, total elastic design. What I mean by elastic design, you can resize your columns and put reinforcements in these structural members in order to remain in elastic phase without any ductility demand, without any damage in the structure. But this costs a lot. And in engineering wise, what we would like to do is to keep the costs in a minimum level and to achieve the best performance from the building. So this seems not feasible for civil engineers. What we do instead, we do ductile design. In nearly 90%, 95%, 99% of the buildings, when you look around where you live, these buildings are designed with ductile design philosophy. What I mean, yes, during an earthquake action, seismic excitation, the building, the elastic seismic forces act on the building. What we do is to reduce these forces to a level, and we design our structure in this reduced amount. Civil engineers will know. I mean, we use behavior factors in range of 6, 7, 8. What we do, we reduce these elastic forces 6 times, 7 times, 8 times, and we design our structures to these forces. At the end, what we have, our structure gets damaged. Plastic hinges occurs in the columns and beams, and the building displaces over the linear phase, I mean in post-elastic phase. And what we have to do to withstand this earthquake is put some ductile connections, details in our structure to resist this earthquake. The building will displace inelastically, but it will not collapse. The main purpose is this. Our building will get damaged after an earthquake, but it should not get totally collapsed. Like the previous photos I showed you in Turkey, the buildings should not be like that. The buildings should withstand the earthquakes. You should go out from the building without any casualties, without any deaths. The primary purpose of seismic design is this. You can buy a house, a flat, anywhere in the world with very large costs, let's say $200,000 for a flat, but just after you sign the contract, if an earthquake occurs and your building can be damaged, and the engineer is not responsible of that, because the engineer is doing what's written on the codes. The codes say that you should design the buildings for life safety purpose. They are not elastic, they will get damaged, but you should get out of the building with life safety. The earthquake loads, seismic loads, are a lot different than the other actions, the general loads, what I mean, the dead load, the live load. Live load means us, the furniture, everything that can be shifted in the building, change place in the building. The wind load, snow load, threat load. The earthquake loads are different than these. Why they are different? Because these loads, other than earthquakes, we call normal loads. And what we do for normal loads is that we design our structure not to get damaged under design loads. So the strength that we attribute to our structural members, the design strength, should be over the design load. But for seismic actions, it's not like that. The design strength is lower than the elastic design force, and we expect damage, as I told previously. This is a graph, a force displacement graph, or you can call it a strength deformation graph, showing how we design our buildings for gravity loads. From the y-axis of this chart, you can see the dead load as the lowest level of load. Then dead load plus live load that can occur, that can come to our building. But we do not design our buildings for gravity loads up to this level. What we do, we have some safety factors. We increase the dead loads and live loads. For example, in Turkish code, we increase the dead load for 1.4 times and the live load up to 1.6 times, and we design our structure to this level. But not only this level, we also have some strength reduction factors. For example, we say that we order concrete to a level of concrete quality, let's say 30 megapascals compressive strength. What we do during the design process, we reduce this compressive strength 1.5 times more. So we have a real large margin of safety for gravity loads. But for earthquake loads, this is not the case. The large earthquake loads act on our building, but we assign less strength to our members, and we want our structural members like columns to go beyond the elastic limit and to deform in inelastic range. What I mean is to get damaged. And what we generally want is, with small earthquakes, like service level earthquake that you can experience one time in a year, we want no damage or very limited damage. With the design level earthquake, which is given in the seismic codes all over the world, we want damage in our building to withstand this damage without any casualties. and with extreme level earthquakes, the building can be non-usable after the earthquake. But again, we want collapse prevention from the building. So what is more important, what we understand here is that the strength, more than the strength, the displacement capacity of our building is more important. Last 20 years, performance-based design philosophy has been implemented in seismic engineering. What I mean by that is that the owner of the building can come to you and say, I want my building to be operational after an earthquake, or I want immediate occupancy. This building can be damaged, get minor damages. Maybe there can be some electricity cutoffs, or there can be some problems with the plumbing system, but I want my building to be in immediate occupancy state after an earthquake. Or they can say, I'm satisfied with the code level, so please design my building in life safety, and the building can be damaged. I am aware that I won't be able to use this building after the earthquake, or yes, I can use, but after some retrofits, the owner can say something like that to you, or the building can be designed to collapse prevention level, which is beyond the code. So we generally want this collapse prevention level for earthquakes more than the design level earthquake. Generally, for a residential building or office building, what we want is that for frequent events like the earthquakes that can happen any moment, which has a probability of accidents of 50% in 50 years, we want no damage. The building should be operational. For occasional events that can happen maybe every 5 years, every 6 years, let's say, which has 20% of accidents in 50 years, we want our building to remain in immediate occupancy level. For rare events which are given in the codes, we want our building to be safe enough that we can get out of the building. The building can be damaged, so this level is called life safety level. And for very rare events that we generally do not design our buildings for, we want our building to be structurally stable. So the problem is this. There are some buildings, important buildings, what we call hospitals, schools, communication centers, power plants. These buildings should be used immediately be in service after the earthquakes. So for these buildings, life safety performance level is not acceptable. So we want functionality in these buildings. Nobody wants a building like that is designed according to the code. The building is there. You don't see any structural damage, but inside everything falls down. The ceilings fall down and cannot be used. We see these kind of things all over the world after the earthquakes. The important buildings like hospitals, in the codes we have something called building importance factor. Maybe you are familiar with that. What we do is we increase the design load 1.5 times than the general buildings. We assume that if we increase the strength like that, the building will stand still, there won't be any damages, and we will use the building afterwards. But the result is not like that. Yes, maybe your building will not get damaged after an earthquake, but when you get inside, you can see something like that in this image. Everything, the ceilings can fall down, the plumbing system can fail, and the building maybe won't be able to be used anymore after the earthquake. These are two examples that we experienced in 2007 in the World Conference of seismic isolation when we went to the World Conference of Seismic Isolation in New Zealand. One of them is Bank of New Zealand, the other one is Statistics House in New Zealand. They are both in the harbor and they are very recent buildings, and these buildings are designed according to the codes without seismic isolation. Then, just a few months before we arrived in Wellington, in 2016, an earthquake occurred in Christchurch area of the New Zealand. It was just 150 kilometers, 200 kilometers away from the epicenter of the earthquake where we were in Wellington. And what we see in those buildings, for example, this one is the Statistics House. The photo is taken from outside. We took this photo. There is no problem of the building visible. But inside, the ceilings collapsed. There were some prefabricated beams. They collapsed. And this building cannot be used anymore. They will demolish this building and reconstruct it with seismic isolation. So the code is not enough. We understand the code is not enough. Then the Bank of New Zealand. Again, we had a check of this building from outside. We couldn't enter. But what we didn't see any damage. Maybe some damage in the staircases, some damages on the shear walls. But what we learned that this building will also be demolished and reconstructed. So we waste money. We waste a lot of money. And also the people there will have to move to another place. So the solution is this. If you can design any building that is disconnected from the ground during an earthquake, maybe exaggerating, but if it is on air during an earthquake, we hang it by balloons, then there will be no problem. But with today's technology, we are not able to do that. What we can do is, now I will show you in the second part, the seismic isolation. I think we understood the problem till this moment. Please, if you have any questions up to this part, let me know. And I will wait maybe half a minute, 1 minute, then I will start with the second part of the presentation where I will tell you about the seismic isolation. Please, if you have any questions, if you have any problems, please send us a message so I will try to reply these questions. So we have one question at the moment. They ask if this video will be recorded and shared. Yes, it is recorded at the moment, and it will be shared afterwards at the website of ED808. Are there any more questions? Yes, I'm waiting for your question. Khalid, I think, yes. The other people, if you experience any problems with the presentation to follow it, please let me know. I just gave you the basic view of the problem, and now I will show you the solution. What software do we usually use for performance-based design apart from ETAP, STEP, Perform 3D? He asks. The softwares are, yes, we benefit from softwares. We use these softwares to reach the solution of our problem. We mostly in Turkey, for seismic isolation projects or the other performance-based design projects, we use the softwares that you mentioned. But there are other softwares as well. I don't want to give names. You can check. I don't want to make the advertisement of any softwares. But the softwares, be aware that softwares are tools. The important thing is that you, the engineers, how you interpret the results of the softwares. If you know how to use this software really, I mean, maybe if you do something really bad, really wrong, the results you achieve may be illogical, that the result may be catastrophic. So whatever software you use, I think the important thing is the engineer. Yes, you gave some names. We mostly use these softwares. After this presentation, if you send me an email, Khalid, I will try to support you in this. But for this moment, I cannot give you some names. If there are no more questions, yes, we have a question more from Said. During earthquake excitation in isolated condition, do we experience shaking much more than not isolated in terms of acceleration or not? Said, yes. During an earthquake excitation, I will tell you now more, but the main purpose of seismic isolation is this: to reduce the accelerations felt during an earthquake. In conventionally designed earthquakes, the ground motion can be increased up to 3 times larger than the ground motion. The main purpose of seismic isolation is to reduce this accelerations felt in our buildings. If you wait a little bit, I will tell you about seismic isolation, and then we can discuss about this at the end of this presentation. Thank you very much for your question. We can start with the second part. Let's see. Let me start the second part. Wait a second, please. We don't have any questions. Okay. Yeah, we have some questions. Okay, sorry for that. I am asked if what are the best codes for seismic isolation, I guess. In the world right now, the best codes for design of seismic isolated buildings could be ASC 716. In Eurocode also, Eurocode as well. Eurocode has 2 parts. In Eurocode 8, it is mentioned, and also there is another part. It's called EN 15129, which talks about seismic isolators. You can use that. Also, at the moment in Turkey, we have a Turkish code for seismic isolation. If I know Mexican code, there is also seismic isolation Mexican code. ASC 41, I'm not so sure, but ASC 41 maybe for it should be the performance-based assessment of buildings. No, I am not so sure about it. But ASC 716 is really good. You can use it. Let's see another question. Can we use seismic isolation system for retrofitting of masonry buildings? You will see the answers of these, but yes, you can use for retrofitting of masonry buildings. There are examples of these on the world. In New Zealand, as far as I know, there are some cases. Also, there are some cases in USA that they retrofitted masonry structures. We can make another presentation that I can show you these examples. For seismic isolation approach, are these done using traditional force-based design or displacement-based approaches used? Displacement-based approaches used, I will talk about these. For questions related to seismic isolation, please wait a little bit. I finish the seismic isolation part and I collect all questions. Okay, again, there is a question for seismic isolation. I will answer this at the end. Let's stop the questions at the moment because they are all related to seismic isolation. Let me finish the part 2 and I will have all the questions. Yes, we can start the part 2. So, now we know the problem, what the problem is. Now I will talk about the solution of the problem. What you can do. If you want your building get no damage, and also you want the non-structural members, the ceilings, the plumbing system, the furnitures, not to get damaged, you can do 2 things. One, you can design your building with higher levels of earthquake loss by using building importance factors of 1.5, let's say. You can save your building structural members up to a level, let's say. You can reduce the behavior factor maybe to lower levels, and you can have larger sizes of elements, and you can save a building. Then this is not enough. When you make a building with, when you design a building with higher earthquake loss, this means that your building gets stiff and stiff. When your building gets stiffer, you attract more acceleration to your building. This means that you will suffer non-structural damage in your building. In order to prevent that, also you have to do seismic design of non-structural members. You have to put money on that. You have to fix every element in order to not to see scenarios like the photos I showed you previously. This costs a lot. Or you can put this all to a side and you can use seismic isolation. What is seismic isolation? You put, you see in the image on the left, you see a conventional building, how it behaves to an earthquake excitation. The building shakes, and during this shake, the stories that are because of the inter-story drifts, the building's elements, structural members get damaged. In the image on the right, we place isolators over the foundation level, and we somehow disconnect the building from the ground. The building over the isolators move like a rigid box, and we do not see large inter-story drifts anymore. The inter-story drifts are very limited, nearly like a rigid box. So we do not see damage on the building. The earthquake always has a demand of displacement from our building. In conventional buildings, like on the left, the displacement is seen on the building. This means damage. For the isolated buildings, the displacement mostly happens in the isolation level. What we do, we put some elements in the ground level between the foundation and the superstructure with very low stiffness in horizontal direction that can the building can move in each direction, in lateral transverse direction, and also it should be very stiff in it should have very high stiffness in vertical direction, so that when the building moves, it should not, the isolators should not get damaged, and after an earthquake, the isolators can be used several times without any damage. So what we do is we put some elements we call isolation units with high stiffness in vertical direction while very low stiffness in horizontal direction. How it works? By doing that, we modify the vibration periods of our structure, and we try to prevent our building from the high frequency destructive vibrations coming from the ground. Sorry for that. So the main benefits are by using seismic isolators, we reduce the story drift, which means the damage in our building. We reduce the story accelerations. That was one of the questions asked. We reduce the story accelerations so that we do not have any problems about the non-structural members as well, like furniture, plumbing system, or maybe even you do not feel the earthquake you do not feel an earthquake, and we reduce the structural membral forces. Here is a real-time movie from a shake table test in Japan in E-Defense laboratory. This is a building with real sizes, which is furnished as a hospital, and the earthquake is a very large magnitude earthquake. Right now, I don't remember which earthquake record was used, but it's a very large and destructive earthquake. And you can see the building is floating on the ground, over the isolators. What we see, normally if it was a conventional building, we would see the damage on the structural members, even in the non-structural members. But what we see only is that the doors, sliding doors, opening and closing, some unfixed and furniture with wheels, they move in the room. Some suspended elements move also, but this is not in such an earthquake, high magnitude earthquake. This is something acceptable. We do not see any damage in our building, nor the non-structural members. This is also another image recorded real time during an earthquake. You see the isolator 1 isolator, the black one, the rubber isolator, and it is attached on a column, and an earthquake occurs. Below, you can see the earthquake record, the lowest earthquake ground motion. The accelerogram is from the ground, the magnitude, and the other one is on the second floor. They placed a accelerometer on the second floor, and they record the accelerations. You can see that the accelerations are reduced less than the ground motion itself. So the accelerations are reduced in an isolated building. And on the top right, you can see the displacement trace of the isolators. Here, what we see is like the ground, the building stands still, but the ground moves. Yes, generally, actually, it is like that. During an earthquake, the ground moves, not the building, but what we think that the building moves. So what we see here is that. Let's move forward. This is also another footage from Japan. The building where there are bicycle racks on the left is an isolated building. Please notice the shoes on the ground, and the earthquake starts to happen. The ground moves, and the building nearly stands still over the ground as a rigid box. You do not see any damage on the building, but the ground moves only. So maybe all of you think that This is a very recent technology, and it is recently being used in the world, but actually it's not like that. By knowing or without knowing, our ancestors used this technology in their designs. I can name some of them. One of them is the tomb of Kirosh in Persian Empire, built before Christ, 506, 530. What they did while building this tomb is that they placed the stones used as a foundation of the tomb on top of each other without using any mortar. So during an earthquake, the stones move on top of each other with friction. And since it is not fixed to the ground, this tomb is still standing still there. So we can call this seismic isolation. Yes, it's not like the ones that we see right now. Maybe the displacement is very low, but definitely it reduces the force acting on the tomb at the top. Or the Roman temples. You can see in several places, maybe in Athens, even in Turkey, you can see examples of these tombs. What they did, over the bedrock, over the ground, they placed sand and they constructed these tombs, the temples over this sand. So during an earthquake, during a seismic excitation, when the ground moves, these temples also move by friction over the sand, and they feel the acceleration, the ground motion, less than a fixed structure. Let's see one more example from the history. The obelisk in Sultanahmet Square of Istanbul. It is not actually definitely, we cannot call it definitely a seismic isolated building, but it's very similar. It has a rocking motion. There are 4 bronze cubes below this obelisk, and during an earthquake, these bronze cubes rock. They make a rocking motion, and this obelisk is very slender, is still there. When you go to Sultanahmet Square in Istanbul, you can see this obelisk there. It's amazing. This is also seismic isolation. When the people start to see this kind of examples in the history, hundreds of years ago, they, of course, with the recent technology, they tried to create the isolators, which are similar to the these days nowadays isolators, and they tried to make some patent applications for these isolators. One of them, in 1870, a French person, I guess, made a patent application for a mechanism having spheres located inside 2 concave surfaces, but it stayed in the patent phase. I mean, it was never applied to a building. Again, in 1897, I guess it's an American person, A. Westwood, again, which is very similar to these days technology, these days friction isolators. He made a patent application for an isolation unit composed of a single articulated block located in concave surfaces. In 1906, in Munich, again there was a patent application for a rigid base plate that moves off solid spheres located under the building, which is very similar to the friction isolators that we use these days. A medical doctor in England made a patent application to be used under the buildings. They, like the temples that I showed you, he suggested to use a slippery mineral that is talc, we call it talc powder, under the building, so that the building moves on this slippery mineral. Then these, up to now, none of them are used in any building. They stayed in the patent phase. But in 1974, William Robinson, I call him the ancestor of the seismic isolation technology. William Robinson in New Zealand invented the first prototype of lead rubber bearing being used today. And he invented, he manufactured, and these isolators are used in the buildings even right now. This is the ancestor of the rubber isolators that we use. And in 1985, Victor Zayas, I think he is right now in United States, in California. Both of them has brands of for their technology. Victor Zayas is right now in America, but he's if I'm not mistaken, he is from Chile. He was born in Chile, and he invented the friction pendulum bearing used today. The first applications of these isolators, these are the primitive applications. They are not lead rubber bearings or friction isolators actually. The first one, which we know, is the Imperial Hotel in Tokyo, in Japan. The building was constructed in 1921, and it survived the 1923 big counter-earthquake with minor damages. And there were rubber pads, not isolators, I don't say isolators, but rubber pads under this building. Very similarly, in 1969, in Pestalozzi School in Macedonia, former Yugoslavian Republic of Macedonia, in Skopje, there was a school, and they placed rubber pads, rubber isolators under this building in 1969. But the problem with this school is still there. The problem with the school was, maybe you can see from the image also, that the rubber pad had some bulges because there were no steel shims. The vertical stiffness of these rubber pads were not high. It suffered from the axial loads acting on it, because it's like the recent, it's like reinforced concrete columns. What you do in reinforced column to resist, to increase the compressive strength, you place stirrups to keep the core concrete there. It's very similar. If you do not place steel shims in the rubber, it makes bulges like that. So after some time, they took these primitive rubber pads from the building, and they placed lead rubber isolators under the building. You can see the photo below there. When they checked the isolators, the first isolators, the rubber pads, the properties of the rubber under this building, they see that the rubber properties did not change a lot during this time. And after 1970s, the first application was in New Zealand, in modern terms, and the first application in United States was after mid-1980s. Several applications have been done all over the world. The top rank with the most seismic isolated buildings in the world are located in Japan, but these buildings are mostly small-scale buildings, like residential buildings of 1-2 stories. And in the numbers of 2011, there were more than 5,000 buildings, seismic isolated buildings in Japan. Then the second ranking was in China, then Russia, Italy, United States, France, Taiwan, New Zealand, and Armenia. These buildings, these numbers are old numbers. They should be updated. As of 2017, for example, here in the chart there is no Turkey, but there are 120 buildings in Turkey as of 2017. and these buildings are quite different than the buildings in Japan or in part of it. They are large buildings. I will show you some examples of these as well. So let's see the effects of isolation to our building. We changed the vibration period of our building by using seismic isolators. The primary effect is period elongation. From the chart on the top, consider a base shear and the period chart. You can think of it like a response spectrum curve, as acceleration on the y-axis and the period on the x-axis. What we design generally for the fixed base cases, we design our structures with low dominant periods. What we do by using isolators is we elongate that period. Normally, for a fixed base case building, for example, 10-story building, the period would be, vibration period would be 1 second, and the acceleration acting on the building would be high, considered to the base isolated case. With base isolation, we increase this period, elongate this period up to 5 seconds. And when we elongate this period, this means that the base shear acting on the building, the forces acting on the building, the accelerations acting on this building is reducing dramatically. But when you reduce this, when you elongate the period, okay, you experience lower magnitude of accelerations, but at the same time, the earthquake demands more displacement from your building. If it is a fixed base building, consider a high-rise building of period, let's say 4 seconds, 5 seconds. The top story displacement would be maybe 1 meter for a high-rise structure, 100 meter high building I am talking about. When the building makes this displacement, you also see damage on your superstructure, in your columns, in your beams. For a base isolated structure, we go nearly to the same periods, 4 seconds, 5 seconds, and the displacements happen only on our isolators. The building over the isolators move like a rigid box. The relative drifts, the drift of the structure is maybe 100 times less than the fixed base case. So the primary effect of seismic isolation is to elongate the period. The secondary effect is to increase the damping, the energy absorption capacity of the building. Normally, when we design our buildings, we design the building for example, for reinforced concrete structures, 5% damping. For base isolated structures, this can go up to 40%. And when damping increases, the displacements get reduced, and also the forces and also the accelerations reduced. So there are two effects of seismic isolation. The first one is period elongation. The second one is the increasing damping capacity of our building. Now I will talk about the main types of isolators that we use in nowadays buildings. The first one I would like to talk about is the rubber isolators. First I start how we extract, how we obtain rubber. Rubber is obtained from rubber trees, geographically these rubber trees are grown in specific regions of the world. For example, top 5 rubber producing countries are Thailand, Indonesia, Malaysia, India, Vietnam. So we can say that these rubber trees need some mild climate in order to be grown. What they do, each factory, each rubber isolator manufacturer company, major ones, have plantations in one of these countries. what they do every day, 2 times a day, they go to the buildings and they scratch the trees and they collect the some rubber extract from these trees. And then they put some chemicals inside and they heat it and they achieve the rubber that we use nowadays, which is very flexible and which is very elastic. And the rubber isolators are composed of this rubber. In the rubber isolators, previously what we said is that we want horizontal flexibility and very high vertical stiffness from our isolators. The horizontal flexibility is achieved by the rubber itself. Think of a rubber string. You pull it and it elongates, and when you leave it, it comes back. So horizontal is flexible, a very flexible material, but it also helps us to when isolator moves, let's say 50 centimeters, it helps us to come to the original point with no deflection. So horizontal flexibility is achieved by the rubber compound, and the vertical stiffness, for the vertical stiffness we need to insert steel shims in this rubber. If you do not insert steel shims, it will be like Pestalozzi screw that I showed you previously. There will be bulges in the isolators. Then we have 3 types of rubber isolators: low damping rubber isolators, high damping rubber isolators, and lead rubber isolators. Here on the figures, on the top right, you see a lead rubber bearing where there is a hole inside the rubber isolator and you insert a lead core inside, which helps us to increase the damping capacity of the isolator. Then on the right down part, it can be both low damping rubber bearing or high damping rubber bearing. That there are no lead cores, but the damping is achieved by the chemicals you put inside the rubber compound itself. In lead rubber bearings, the damping ratio is between 20% to 30%, and the damping occurs by the yield of lead plug itself. Why we use lead plug? Because after it yields, it can return back to its original form again, and can be used again and again. For high damping bearings, the damping ratio is between 10% and 20%, and the damping is achieved by adding some chemicals, what we call carbon black, inside the rubber compound itself. Here we say it is up to 20% for high damping rubber bearings, but as far as I know, some of the main high damping rubber bearing manufacturer companies in Malaysia and as far as I know in Japan, they achieve more than 20%, 20 to 23% damping for high damping rubber bearings. Low damping rubber bearings are not used solely. They are mostly used with additional dampers, because what we said, there are two benefits of isolation. No, one is period elongation. The second one is additional damping. If you do not benefit from the damping of the rubber itself, then only period elongation in most cases is not enough. So what we do, we use these low damping rubber isolators with external additional damper systems. For example, on the right top, you see some red element. This red element is the friction isolator. In one part is connected to the superstructure, in the other part is connected to the foundation. So when the superstructure moves over the isolators, in the joint in the middle, it dissipates energy, and we achieve additional damping like that. In the bottom part, with green things are the hysteretic dampers, still hysteretic dampers, and when the superstructure with the, you can see the blue beam, when it moves, this still hysteretic dampers yield, and they dissipate energy. And after the earthquake, you need to change these still hysteretic dampers. They are low cost, but they need to be replaced after an earthquake. For the rest, you don't need to you don't need to do any replacements. The isolators, if they are designed well, you do not need to replace the isolators. Let's see a video from a test. It's a rubber isolator test, which was done in Italy in EU Center. There is a shake, something like a shake table that is moved. There are 3 cycles. You pull 3 cycles up to a displacement, and you make 3 cycles, and you increase the displacement, and you repeat the test. And on top of it, there is a pressure, axial load pressure, and as far as I remember, for this case, the maximum axial load was around 10,000 kilonewtons, which is 1,000 tons. 1,000 of tons of pressure on top of the isolator, and the isolator will make a maximum displacement of 375 millimeters, nearly 40 centimeters. This is a small scale isolator. 1,000 kilonewton compressive stress, compressive force on it means that you can take that an average car today is nearly 1 ton, maybe 1.5 tons. This means that there are 1,000 cars on this isolator, and it displaces up to 40 centimeters. This is another footage from a shake table test, a real scale building which is used as a hospital again. And let's see, on the bottom left, you will see the rubber isolator, and on the right, it's a CL linear bearing that it moves. It's like a friction bearing, but it helps also to reduce the lateral stiffness of the isolation system. Let's see how it behaves. Sorry for that. Let's see how the building moves over the isolator. This is again a very large earthquake, and you can see that what happens is only that the things that are not fixed with rollers, they move in the building, but the building is not getting any damage, and the displacement is maybe 50 centimeters, plus minus 50-60 centimeters. It's great. Sometimes we are using these rubber isolators in combination with other type of isolators, like flat sliders, because in some parts of our building we want very low lateral stiffness. For example, in this case, it was a hospital, retrofitted reinforced concrete hospital, that the main isolation interface was on the ground floor, and the rubber isolators were placed under this ground floor over the columns. But there were also elevators and staircases, and you cannot interrupt the elevators in that isolation interface level near the ground level, because think that if an earthquake occurs at the moment that the elevator cabin is on the level of isolation interface, it can get damaged. If there are people inside, they can get hurt. The isolation system maybe will not work. So what we did is we installed isolators with very low lateral stiffness below this elevator case walls in the foundation level. So it is, think of the superstructure. The superstructure starts from the ground floor, then it goes down to the foundation level, and it goes up again on the ground floor. So it will move, the elevator walls will move with the ground floor slab. Therefore, you need to put seismic gaps in the lower basement floor to accommodate the displacement of the isolated building. The second type of isolators is the friction pendulum isolators. It actually has a very simple mechanism. You all know this mechanism. It's a pendulum movement, and everything is very basic. I mean, all the formulations are also very basic. You have a concave surface, and you have a sphere on this concave surface that moves, and on top of it there is another cover plate, and you place the building over this isolator. Why we need a concave surface? Because think of a rubber bearing first. If an earthquake occurs and this isolator moves 50 centimeters, what is the thing that retracts it back? The rubber itself, no? It's an elastic material. So when it elongates, it pulls it back to the original position. For friction isolators, if you put it on a flat surface, then if the building moves 50 centimeters, this means that it won't be able to come back. But if you make it on a concave surface, then it goes up a little bit, and with the potential energy returning to kinetic energy, it wants to return back to the original position. So therefore we use concave surfaces. The friction isolators have mainly three types. The first invented by Victor Zayas was the single concave pendulum isolators, which has a concave plate on the bottom and a sliding part on top, and the cover plate on top of it, and the building was going on the isolator. The problem was this: the displacement capacity of the isolator was very limited, because if you want to make large displacement, then you need to have a very large isolator. And also, during this friction, during this movement, due to the friction, the sliding material gets very hot. By hot, I mean more than 200 degrees Celsius. And in order to reduce this temperature increase, they also invented double concave pendulum. In double concave pendulum, the displacement capacity is doubled, plus also the heat effect is reduced, maybe half. So in the high seismic regions, we use mostly double concave pendulums. You can see on the right bottom photo that the shining part is the stainless steel, and on top there's a sliding part which is black. This black material is actually a PTFE based material, Teflon based material, and they add some additional elements more in order to make it high resistant to friction, high resistant to temperature effects, and high resistance to the axial load. So they call it ultra high molecular weight polyethylene material. So this is a patented technology. Actually, it is very simple to have a concave plate and to manufacture these isolators. If you have a CNC machine, you can do it, but the know-how is on this friction material. And then we have triple friction pendulum, which has a patent at the moment by Victor Zayas' company in United States. The triple friction pendulum doesn't mean that the displacement capacity is tripled. It is very similar to the other ones actually, but the thing is that Uh, think of friction mechanism. Think of a table staying on the floor. If you want to move it, and with some load on it, axial load on it, if you want to move it, and if you increase the lateral force to this desk slowly, after some time it starts to move. No, it's very similar to that in the friction isolators. They have a friction coefficient, let's say 5% of friction coefficient, which means that the isolator will not move until the friction force is beaten, which is the axial load times the friction coefficient. If you have 1000 kilonewtons on the isolator, then times 5% friction coefficient, until that force level, the building will behave like a conventional building. So this means that with minor earthquakes, with small earthquakes, your building will behave like a rigid building, will behave like a conventional building. After a point, it will start to move, and then you will benefit from the isolation effect. For triple friction pendulum isolators, the main benefit is that inside there is a inner core which has very low friction coefficient, less than 1%. The outer parts, the outer friction coefficient at the outer articulated parts, the friction coefficient is 5%, let's say, but the inside it is 1%. So with minor earthquakes, with small earthquakes, small magnitude earthquakes, even with them, the isolator moves. So you do not feel the effect of earthquakes. You feel less with triple friction pendulum isolators. Here is a comparison between single pendulum bearing and triple pendulum bearing. On top, you will see the friction isolator moving on one articulated surface, one concave surface. On the double part, you will see that the first motion, I'm repeating it, the first motion starts in the inner part with low friction, while the second movement second and third movement starts on the upper plate. Here is a test video that I recorded during one of the tests of triple friction pendulum. You will see how the inner part moves and also how the isolator moves. Notice that the first movement starts at the inner part. Then the outer it moves at the outer concave surface. And right now it's a small scale earthquake again. Well, when I say small scale, it is maybe 70 centimeters. It has 70 centimeters diameter. I don't remember right now. It has maybe more than 10,000 kilonewtons on it, and it moves probably 50 centimeters in each direction, plus minus 50 centimeters. And this is a very similar shake table test footage for a friction isolator, again a hospital. You see the building moves. Again, the unfixed elements move in the building, and the isolator moves nearly 67 centimeters. I repeat it again. Check now. It starts to move slowly. Then right now it is nearly 70 centimeters maximum displacement. The different thing in isolated building design is that when you do a conventional building design, what you do as test is you only take some samples in the site, you cure them in the laboratory, and you do some compressive tests. No? Do you think that this is enough to understand the situation in the building? I don't think so. For seismic isolators, since these are crucial elements for the building performance, what we do, we test them. We apply two types of tests on these isolators. One of them is prototype test. The second one is manufacturing test. The prototype test, you take two samples of each isolator type and each isolator site, and you test them under extreme conditions. The maximum factored loads, axial factored loads, and the maximum displacement. You do several tests, and at the end of this test, you don't use these isolators anymore. You just throw them away. The second kind of test is the factory production test, the manufacturing test. In USA, 100% of the isolators that will be used in buildings should be tested for after manufacturing. What you do, not like the prototype test, not in extreme conditions, but with less axial loads and with less displacements, maybe with lower speed, you test these isolators, and if they match your target, then you say, okay, I'm using these isolators, I can use these isolators in my site. So you pack them and you send them to the construction site. In Eurocode, in Europe, this is a little bit different. The prototype test is very similar, but the factory production test, what you do for friction isolators, randomly you choose 5% of friction isolators and you test them. For rubber isolators, randomly you choose 20% and you test them, and if they're okay, you send it to the site. In Turkey, it is 30%. You select randomly if it is friction isolator or rubber isolator, doesn't matter. You select 30% of isolators and you test them, and if they're okay, you use them in your site. Factory production tests are mostly done at the factories, the manufacturing plants. Most of the manufacturers have their own testing equipments that they test the isolators. Mostly they are slow speed tests, but we accept these results for the factory production tests. But for production tests, they need to be real-time tests. What I mean is that what you will see during an earthquake, the speed should be the same. The axial load should be the maximum. The displacement should be the maximum. So the laboratories are very limited to do this prototype test. Mostly, we also prefer these tests to be in the independent laboratories, mostly in some universities or other private testing facilities. But sometimes these tests are also done in the facilities of the manufacturer. Here you will see a table with the laboratories. One of the largest and the most popular is the testing facility in San Diego, which has a 53,000 kilonewtons of vertical force capacity and 8,900 kilonewtons of lateral load capacity, and the displacement capacity is plus minus 1.2 meters, and the speed capacity is nearly 1.8 meters per second. It's really good, and the advantage of this laboratory is also it has a 6 degree of freedom testing facility, which means that you can give a real earthquake record and you can see the real performance of an isolator in this testing facility. The second largest, the second most preferred one is in Italy, in Pavia, in EU Centre, EU Center, how you call it. The axial load level is quite the same, but the displacement capacity is less. It's nearly 50 centimeters, the displacement capacity, and the velocity is quite good, again 2.2 meters per second. Then there are other small-scale laboratories all around the world. The highest capacity is seen that they are mostly the testing facilities of the isolator manufacturers, so they are not independent. I will talk about some of the seismic isolation applications, and I will finish this webinar. By April 2015, this was the total isolated building projects all over the world. So here in the ranking, Turkey is there, but right now it is more. The largest again is Japan with 7,800 buildings. Then China, then United States, and it goes on. One application, high-rise building application in Japan, different than the rest of the world. Normally, we do not want high-rise buildings to be seismic isolated. Why we do not want? Because we do not benefit from the seismic isolation very well. Because normally this, what I said previously, was the first benefit of isolation system is the elongation of the period. High-rise buildings have already long periods, so you do not benefit really from long period. You only benefit from the damping of the isolators. And the other drawback for applying this isolation technology to the high-rise building is that since these are slender buildings, there can be some uplift or high tension forces on the isolators. We do not want these. The isolators can get damaged with tension forces or uplift forces. Mostly the codes restrict this. But in Japan, they somehow solve this problem with different kind of solutions. For example, sometimes they use isolators plus dampers on the superstructure, viscous dampers, friction dampers, to keep the tension forces and uplift forces lower. Or like this in this case, they tied the isolators with some kind of strings that during an earthquake, if there is an uplift occurs, they pull it down. One other example, again in Osaka, again a high-rise building with seismic isolators. One example here, probably again in Japan. Here you can see the isolators on the parking space, very large columns, and on top there are isolators, and the building goes on. This example is typical. As I told you, the largest number of isolated buildings is in Japan, but most of these numbers is like the buildings like these, very small Japanese private houses with isolators below. Again, a Japanese private house which is using isolators, different type of isolators underneath. This example is from Sochi, a high-rise building example, 21-story building, again with isolators. One in Italy, in Foggia, a building with isolators. You can see black isolators. They installed isolators in different parts of the over the basement floor. Again, one other building in Italy. One interesting building application in Armenia, in Yerevan. Probably they did not have large molds for large-scale isolators, so instead of putting one large isolator, they installed 5 small isolators underneath one column in this building. This one is one of the best, one of the ones that I like the most. It is from Italy again. It's called CASE project. After 2009 L'Aquila earthquake, the city center got damaged. There were so many masonry structures and they were mostly damaged. So these buildings are constructed in a very short time, like 6 months time, and they were prefabricated. They installed very fast, rapidly steel columns, and on top of them they installed isolators and the post-tension slab on it, and they put the buildings on top of it. They can be steel buildings, wooden buildings. In some of them were reinforced concrete buildings without trying to coincide the columns with the columns of the superstructure with the columns of the substructure. Again, one photo from that building. And I will conclude with the world's largest base isolated buildings that was listed in Engineering News Report magazine in July 27, 2017. And the number one largest building is the new headquarters of Apple in Cupertino in California, which is 445,000, covering 445,000 square meters area, and it is the world's largest base isolated structure at the moment. And it's a prefabricated building. They constructed it again very fastly. The prefabrication system is very good match with seismic isolation. Since the displacements on the superstructure is very low, you can use prefabricated buildings easily without any problem and very fastly. So this is the largest building on the world on base isolation by 2017. Right now, for example, what I know in Turkey, in Istanbul, there is a hospital project in Istanbul in İkitelli region. It's called İkitelli Hospital. It covers more than 1 million meters square closed area. It's huge. It's enormous. It's not in this list, but it will be probably in service in 2020 or 2021. Right now, it's under construction. The second building is from Turkey, Adana Health Complex. It is covering 430,000 square meters of area. Over the foundation level, there are the columns with isolators, and there is a continuous flat without any gaps of nearly 300 meters to 300 meters, and on top of it there are the blocks. So this is the second largest building, and it's in service right now with 430,000 square meters of closed area. The difference of the area is very low. I'm always saying that if the owners of this hospital, if the government of Turkey did know that there would be a magazine, there would be a list like that, probably they would have an extra small room, and they would catch the Apple building as well. The third building is in Tokyo, a high-rise building, Tokyo Sky 3 East Tower. It covers more than 200,000 square meters of closed area. The fourth one, again in Turkey, you will see several hospital applications from Turkey. Let me tell you why it is like that. Because in 2013, with a unique regulation, there is no other example of that. The Ministry of Health said that all the buildings, all the hospital buildings that will be constructed in Turkey in seismic regions should be constructed with seismic isolators. And from that time, so many health campuses over Turkey, city hospitals over Turkey, is being constructed with seismic isolation technology. These are huge hospitals. These hospitals will serve a large region near them. So they are in the list. the hospital that I told you, 1 million meters square, is also one of them. So the fourth one is from again Turkey, in the city of Sparta, covering more than 220,000 square meters of closed area. Fifth one is in Japan, in Tokyo. It's a logistics center, logistics park Hino is called. It's a 5-story building. It covers more than 200,000 square meters of area. Sixth one, again from Japan. It's called Logiport Sagamihara. It's a 5-level warehouse building covering more than 210,000 square meters area. Seventh one, again in Tokyo. You see lots of buildings from Japan. It's Shinagawa Season Terrace in Tokyo. It's covering more than 205,000 square meters of area. It's an office building. Eighth one, from Turkey, the second airport of Istanbul, in the Asian side of Istanbul, Anatolian side of Istanbul. It's called Sabiha Gökçen Airport Terminal. It's right now in service. It's it's covering 200,000 square meters, and it is seismically isolated. The ninth one, again from Turkey, in the Erzurum region. It's one of the first seismic isolated hospitals in Turkey. It's covering more than 180,000 square meters of area. What I want you to notice is that normally for seismic isolated structures, we do not want this kind of different geometries. If you notice the buildings in Japan, they are all rectangular shape or square shape, but the ones in Turkey is in different structural forms. These are not really suitable for seismic isolation, but somehow they are done like that. And the 10th one is again this one from Taiwan, a medical center which is covering more than 157,000 square meters of closed area. This is the end of my presentation. I will collect your questions. I guess that you have several questions. After this presentation, if you have any other more questions, you can write me an email. I will try to respond to you as soon as possible. I may not be able to respond very quickly, but I be sure that I will respond you back. And I would like to thank you all for participating in this webinar. And also I would like to thank you as a host to ED 808 for giving me this opportunity to reach you. I hope you enjoyed it. And let's see if you have any questions. Let's see. Now, let's see that the previous questions, there were some questions regarding the seismic isolation. Please write questions that you have more insight. Write me and I will try to answer. One of the questions was, for seismic isolation approach, are these done using traditional force-based design or displacement-based design approaches used? Lawrence Galvez asked this question. For seismic isolation, we do not prefer force-based design. We use displacement-based approach for the design of isolated buildings. Somehow, we also check the isolators with force-based design approaches as well. The question comes from Bilal Baran. I think he has left, but let's see. How do you use seismic isolation on the soft soil? Periods long and building can be in resonance. What is the solving for this problem? For soft soils, it will be very similar to the conventional buildings as well. To be used in the soft soils, first of all, you need to make a soil improvement. And you need to improve the soil properties. And you need to get rid of these soft soil properties. Then, afterwards, you can use seismic isolation. Yes, if you build a building seismic isolated building on soft soil. Since the isolated periods are long, the building can be in resonance. So therefore, I do not recommend to use seismic isolated buildings on soft soils. Mr. Khalid asked one question. It is very customized for performance design, as you mentioned, and talks about isolation as well. He thanked me. Thank you very much for your participation and your questions and your attention. You had some extra questions, I know them. Let's keep in touch, and I will try to help you as much as I can do. Any more questions? Let's see. Let's wait one more minute. And I'm contented with the participation of this webinar. Thank you very much all. Yadin asked a question. Thank you very much for your nice presentation. How to fix the target period of the isolator for its design? Actually, this presentation was the introduction part. If we continue with ED808, I would like to show you as well how to design isolators, how to fix the target period, and how to achieve them. This is the content of some other presentations. I cannot give you the answer right now for this webinars. I'm sorry for that. If you have any questions regarding that, you can ask. I can give you some sources for that, or we can organize another webinar and I can show you how we design isolators and also how we fix the target period. Muhammad asked a question. Is there any PDH for this term? PDH? You know?
No, not PDH. No.
What's PDH?
Per during hour. It's a factor for certificate, I guess.
No, we don't have it. We won't give it. Sorry, Muhammad. Mr. Nazif Yazan asked a question. Thank you so much for this presentation. We will wait the new one. Thank you, Mr. Nazif Yazan, for participating. I'm also very happy about this webinar, and I'm really very glad that you also enjoyed it. One more question or comment from Khalid. It will be my pleasure to keep in touch with you. I will be also happy to visit my works on seismic field through the blog. Okay, thank you very much, Khalid. I will check it for sure. Thank you very much for your participation and your attention. Ismail Saka thanked me in Turkish. Thank you very much. I hope to meet you sometime, and I hope to assist you if you have any questions further. Thank you very much, Khalid. I think we are done. Okay, thank you very much for your attention again, and hope to see you again. And once more, I thank ED808. One more comment, I guess. The comments are coming from Lawrence Galvez. Very substantial learning in seismic isolation will be my I'm very glad that you benefited from that, Lawrence, and I wish you best luck on your research on bridge isolation in Philippines. It's very similar concept. I talked about the buildings, but in bridge isolation, it's very similar concept. So you can apply whatever you learned in this webinar. Majid thanked me. I thank you for sparing your time in this webinar. Mr. Ismail Saka asked if we could have the recording of this webinar. For sure, they will. ED808 will send you the record of this webinar. You will have it. Yadin asked a question. Is there any issue? Is there any issue with stability due to overturning for base isolated building? Yes, you should check this, Yadin. Overturning is one of the biggest concerns for us. Therefore, we do not want to. We are not in favor of applying isolators to high-rise buildings due to the overturning forces. So you need to check your isolation system, your building, for overturning forces. It's important. You need to check it. Therefore, we want buildings on with low slenderness ratio on large areas, large buildings with low height. Any questions? Any more? As I told, again, if you have any further questions, you can write me an email further. I think we are done. Thank you very much for your attention and for your participation again. Have a nice evening, day, wherever you are. Thank you.